Hello, I will talk about special relativity. There are three phenomena that occurs when someone is traveling at very high speed, close to the speed of light. The first phenomenon is the increase in mass. The second is length contraction. And the third phenomenon is time dilation. I will start with the increase in mass. Suppose the twin brother who goes on a journey in space weighs 98 kilograms. So the weight is equal to the mass times g, that is the gravity on Earth. The gravity on Earth that equals to 9.8 meters per second squared. So 98 kilograms equals to the mass times 9.8, and the mass equals to 10 kilograms. So the mass of the twin brother that goes to the spaceship towards the star Epsilon, his mass on Earth is 10 kilograms. Okay, so I will explain what is exactly G. G equals to 9.8 meters per second squared. I will explain the meaning of that thing. If you drop an object from the roof of a high-rise building, the velocity of the object will be 9.8 meters per second in the first second. In the second second, its velocity will be 2 times more, that is 19.6 meters per second. And in the third second, its velocity will be 3 times more than the first second, that is 89.4 meters per second, and so forth. In the 10th second, its velocity will be 98 meters per second. In conclusion, every second, the velocity of the object will increase by 9.8 meters per second. Okay, so now I will explain the equation of the mass increase. M equals to m naught divided by the root of 1 minus v squared divided by c squared. So m is the mass of the object or of the twin brother, for example, that flies on the space in the spaceship at very high speed. And m naught is the rest mass, that is to say, the mass of the object or the man on Earth when he is not moving at all. And we divided it by the root of 1 minus the velocity of the object or the man that is traveling the spaceship, divided by the velocity by the speed of light. Okay, so in our example, as we have already seen, so that the mass of the twin brother on Earth is 10 kilograms, his weight is 98 kilograms, and his mass is 10 kilograms on Earth, and we divide it by the root of 1 minus his velocity in the spaceship, that is 240,000 kilometers per second squared, divided by the speed of light squared. So we get the final result of 16.33 kilograms. So we see that his mass, the mass of the twin brother, when he is traveling in the spaceship at the speed of 240,000 kilometers per second, his mass increased to 60.33 kilograms from 10 kilograms. So actually there is an increase of 63.3% in his mass. So according to the mass increase equation of special relativity, or according to that equation, his mass in space will be 16.33 kilograms, but he himself will not feel it, and if his twin brother has a mass detector, the detector will measure 16.33 kilograms. So if he had a mass detector and he measured the mass of his twin brother when he is in the spaceship and traveling towards the star Epsilon in the speed of 240,000 kilometers per second, he will measure his mass that is 16.33 kilograms. Okay. Now I will talk about the second phenomenon that occurs when someone is traveling in space at a very high speed. The phenomenon is length contraction or shortening of the distance. When you measure a distance between two objects that are not in motion relative to each other, let's assume that you measure a certain distance. So that distance between them will shrink when one of the objects moves towards the other object at very high speed. For example, as mentioned, the distance from Earth to the star Epsilon is 10 light years. Yes, L naught equals to 10 light years when you measure it from Earth. Okay, first of all, I will explain the equation itself of distance contraction. L is the distance between two objects, that one of the objects is moving towards the other object at very high speed. And it equals to L naught. L naught is the distance between that two objects when they are not moving relative to each other or when they are at rest. And when we multiply it by the root of 1 minus the speed of the object that is moving towards the other object, and we square it and divided it by the speed of light squared. Okay? And in our example, the distance between Earth or the spaceship to the star Epsilon was 10 light years, and we multiply it by the root of 1 minus the velocity of the spaceship squared divided by the speed of light squared, and we get the result of 6 light years. So we see that there is a distance contraction between Earth and the star Epsilon because of the fact that the twin brother is moving towards the star Epsilon in the speed of 240,000 kilometers per second. Okay, but you should remember that our sun is not moving relative to the star Epsilon, because the sun and the star Epsilon move as one unit around the center of the galaxy, but the distance between them doesn't change. So I will explain it. Suppose that my thumb is the solar system and my finger is the star Epsilon, and my fist is the center of our galaxy, the center of the Milky Way, and actually the sun and the star Epsilon revolve around the center of our galaxy and around the center of the Milky Way as one unit. So the distance between them doesn't change. So the distance between the solar system and the star Epsilon doesn't change because they are moving like that. Okay, so in that situation, the distance between the solar system and the star Epsilon is 10 light years. But when you measure the distance from the spaceship that moves in the space at the speed of 240,000 kilometers per second, then the distance will be shrink to 6 light years only from the point of view of the twin brother flying in the spaceship. Okay? So when the twin brother in the spaceship is traveling at the speed of 240,000 kilometers per second towards the star Epsilon, the distance between the spaceship and the star Epsilon will shrink to 6 light years only. Okay? But in addition to that, the height of the man in the spaceship also shrinks. And if on Earth his height is 1.8 meters, L naught equals to 1.8 meters, then from the point of view of the twin brother who remains on Earth, the height of the twin brother in the spaceship shrinks to only 1.08 meters. I will explain the equation of the contraction of the length. L is the height of the object when it is moving in the space or in the spaceship, and L naught is the height of the object or the twin brother on Earth. And in our example is 1.8 meters, and we multiply it by the root of v squared divided by c squared. V is the velocity of the object or the twin brother that is moving in space at very high speed. So you should know that the height of the object or the twin brother in the spaceship will change anyway when it is moving towards the star epsilon. But if the movement is not very fast, the change will be so small that we cannot measure it, so it must travel in the space or the spaceship at very high speed, close to the speed of light, in order to measure a significant change in the height of the object or the twin brother. Okay, the same rule is for the length contraction. It is the same equation, and it is the same when someone is moving in the spaceship or object or the twin brother is moving towards the star epsilon. Even if he moves at a small speed, there will be very little change in the distance between Earth and the star epsilon. But if we want that the change will be significant, he must move at very high speed. In our example, he moves at a speed of 240,000 kilometers per second. Okay? So, as I already said, it is the same equation for the contraction of distance and the length contraction of the body or the object. We use the same equation in order to calculate the length after the contraction. Okay? Now, if the twin brother that stays on Earth had a height detector, then the detector would show a height of only 1.08 meters, but the twin brother who is in the spacecraft doesn't feel that he is shorter. Okay? Now I will talk about the third phenomenon that occurs when someone is traveling in space at very high speed. And the third phenomenon is the time dilation. As mentioned, from the point of view of the brother who is on Earth, his twin brother is moving in the spaceship at very high speed. Therefore, the rate of time flow in the spaceship will be slower than the rate of time flow on Earth. While on Earth it took 25 years for the twin brother to return from a journey in space, in the spaceship the total time that it passed is 15 years only. So first of all, I will explain the equation for time dilation. T is the total time that is passed in the spaceship during all the journey of the object or the twin brother, for example. It equals to T naught. T naught is the total time that is passed on Earth during all the journey. And we multiply it by the root of 1 minus v squared divided by c squared. V is the speed of the spaceship or the object that travels in the space at very high speed. And c is the speed of light. Okay, so in our example, the total time that is passed on Earth during all the journey of the twin brother from Earth to the star Epsilon and back from the star Epsilon to Earth is 25 years. And we multiply it by the root of 1 minus the velocity of the spaceship, that is 240,000 kilometers per second. And when we divide it by the speed of light, so it 240,000 divided by 300,000, the result is 0.8. And when we square 0.8 and we get in total 0.36, and the root of 0.36 is 0.6, and when we multiply it by the 25, the final result is 15 years. So in the spaceship, the total time that is passed is 15 years only. So because of the fact that the rate of time flow in the spaceship is slower than the rate of time flow on Earth, so there will be the phenomenon that is called time dilation. And the total time that is passed, will be passed in the spaceship will be less than the total time that is passed on Earth. Okay, so while from the point of view of the twin brother who embarked on a space journey towards the Epsilon star, he is at rest and the Epsilon star is moving towards him at a speed of 240,000 kilometers per second. Therefore, in this situation, there will be a contraction of distance according to special relativity, and the total distance between the Earth and the star Epsilon will be 6 light years only, and the round trip distance is 12 light years, and at a speed of 80% of the speed of light, the entire journey in a spacecraft will take 15 years due to the contraction of the distance between the spaceship and the star Epsilon as mentioned. So now we will analyze the total time that is passed in the spaceship from the point of view of the twin brother that is on the spaceship and traveling at very high speed towards the star Epsilon. From his point of view, he is at rest and the star Epsilon is moving towards him at the speed of 240,000 kilometers per second. So in this situation there will be a contraction of distance between him and the star Epsilon, and the total distance between him and the star Epsilon will be 6 light years only, and the total way back and forth from Earth to the star Epsilon and from the star Epsilon to Earth will be 12 light years. So the total way is 12 light years, and when we divided it by the speed of light, we get the final result of 15 years. So the two twin brothers agree that the total time that is passed in the spaceship is 15 years only, and it is 10 years less than the total time that is passed on Earth during all the journey. Okay, thank you very much.